No. Thank you, though.
You're very relatable, you know that?
Well, hey, we gotta have fun, right? Especially, I mean, this is kind of complex material, so if you're not having fun at it, you can be pretty miserable. Okay, so while we're, it's already heated up, so that's good. Okay, any questions I can help you guys with? Anything about class, course, anything? Did you see that I pushed off Wawa 8 to Sunday? I thought you could use another day. And apparently there's some sort of research thing going on tomorrow. Right? So I don't know all the details because apparently I'm not on that email list. So I didn't even know about it until this morning. Okay, go ahead. Go for it.
So anyone who has gotten funding from the university or is in a class that requires a final presentation has to present in the Arts and Sciences Symposium.
Okay.
So the art pieces are going to be in Maudlin. There's going to be an art show by all the seniors that I'm friends with. You should go see it. The opening is tonight. You get free wine and food. And
excellent. That sounds
then
like fun.
tomorrow, starting at like noon, I think, till like 5 p.m., you can go to the Jepson Alumni Center.
Okay.
You know where that is?
I do know that.
Okay. And there's going to be poster and PowerPoint presentations. I'm doing a poster.
Excellent. Sounds like fun. Well, I'll tell you what. So labs are on Friday, and apparently from what I heard from the students is that typically the labs are scheduled for less amount of time on Friday.
Yeah.
So I'm not sure how all that works. So what I'm going to do, and I'll put out an announcement on Canvas later, is I'm going to make lab optional tomorrow. So you guys decide for yourself what you want to do. I will be there, okay, at the regular times. Come to whatever lab works for you. If you feel like you want to go to spend the day at the research, I'd encourage you to do that. You don't have to come to lab. I will make sure to put together tonight all the materials that we would be doing in lab, so that if you want to just do lab at home on the weekend, I don't see any reason why you can't do that. I mean, pretty much there's no difference between sitting at home in your dorm room with headphones on or sitting in a lab with headphones on. So I'll be available to you through the weekend, so if you have questions, you can text me, whatever. If you want to come to lab, that's great. I'll be there. If nobody shows up within the first 15 minutes, I'm going to my office. I can tell you that right now. But if folks do show up, then you can go right through the videos and I'll hang out and be there with you. Okay? Does that sound fair? But I don't want to go through and start redoing all the times at this late date because I'm not even sure what I do or what would happen.
It still start at 1:30. Our other classes get shifted. So like the 12 p.m. ones are getting shifted to 12:40.
Okay.
And then they last till 1:20.
Okay. Yeah, that's just a lot of work. So and so I figure you can hit Canvas, you can get the videos, you can study what you need to see. Everything you need to do Wawa 8 will be in those videos. So and again, I don't see any difference between doing it in the lab or doing it at home, really. The only difference is that I won't be there in your dorm room, and you're probably glad that I won't be. So but feel free to text, and I'll help you out if you have any questions. Okay. And then it'll be due Sunday night. Okay, in terms of the, boy, that is an allergy type of sneeze right there. Huh?
Crazy.
Yeah, it's coming down in layers.
My car,
Yeah.
car's green.
Yeah,
It is yellow.
yeah, my car's yellow too.
Oh, I
Yeah.
fully wiped off my dresser in my room yesterday. It's under a window, would have been open for 20 minutes, and there was a layer of falling.
Yeah, yeah.
This is so
It's terrible. I know. And I was going to go to the car wash, have my car wash, and then I just got this feeling of learned helplessness. It's like, well, what's the point? It's just going to be, in 2 days, it'll look just the way it does now. So I'm in this sort of no man's land where my car looks terrible, but I don't know quite what to do with it right now. Yeah.
Deb and the equestrian team's having a car wash on Saturday, 11 to 4. If you want tickets, $5 to be in.
That's pretty good. That's pretty good. Okay, let's see what else. We're almost done with this course, you guys. We got one more lecture after today, and then we'll do. Don't cheer too loud. You don't want to demotivate me at this point. Right? And then we'll do a review probably next Thursday. We might be finishing up a little bit of non-parametrics on that Thursday. It just depends how far we got. That's pretty much it. Who's taking 300? Right? Okay.
Taking
4 something, 3.
It's with Lambert.
So apparently in 300, my understanding is you guys get to design your own research project. right? In other words, doing it exactly what we've been doing in here. So you had better do well in 300. You have to give me a test run in here, right?
Otherwise, you're going to come back to Virginia.
Oh, I'll haunt you. I'll check with all the faculty. I still have your email addresses in Canvas. I'll be like sending you an email like, that thing about the p-value? So, no, I'm kidding. I'm done. I'm gone. So, but hopefully, I do hope, though, that when you get to 300, that it will feel comfortable to you. Because in talking with the faculty, we had a meeting last night about it. I think the consensus was that some students kind of walk out of 200 really comfortable with what they need to be able to do in 300, but then there's a bunch that really aren't that comfortable. And so the problem is, and it's not about the students. It's really about how to present a lot of pretty complex material in a way that's palatable, knowing that you won't master it in 200, but you should know it well enough so that when you get to 300, you'll have more than just a passing familiarity with the concepts, right? That you'll actually, like when you hear about regression, you'll know what to be looking for in regression. You'll know why you want to run an independent samples t-test rather than a dependent samples t-test. All of those things, okay? And so if you're at the point where you're still a little foggy in that, don't worry, there's a lot of folks who are also foggy. But try to, I would say, as a useful piece of advice, try to review this stuff over the summer so that when fall comes, and you're taking that 300 course, you're feeling more comfortable with things, okay? Okay, you guys ready to learn about regression today?
Sure, sounds great.
Okay. So fun stuff. We're going to go from correlation to regression. We have a fair amount to cover in today's lecture. I'll be giving you conceptual background, some examples. We're going to talk about that Challenger case. And hopefully by the end of this, you'll have a pretty good idea what regression's all about. Interestingly enough, you might be asking, well, why is it called regression? I mean, why use the term regression? Well, Francis Galton did a study, a paper looking at inheritance of height. And what he found was that basically children of tall people tended to be shorter than their parents. Children of really short people tended to be taller than their parents. And what he coined the term at that point was regression to the mean. Okay, so that the offspring regressed back toward the mean from the extreme value that their parents had, either being really tall or really short. Okay. Now, what happened over time was that psychologists co-opted that term to use it in the way that we're going to use it here, called regression. But it doesn't have a whole lot to do with regression to the mean anymore. Basically, what regression refers to these days is the ability to predict scores on one variable when we know scores on another variable. Okay? So we'll use the term regression when we say, for example, we're regressing the dependent variable on the independent variable. Basically what we're saying is we're going to have an independent variable that predicts scores on the dependent variable. We say that the dependent variable is regressed on the independent variable, or set of independent variable predictors. Okay? So the term itself is a little bit obscure, and it comes from research that doesn't look a whole lot like what we actually will consider today. So, but like a lot of things in statistics, there's some obscure history there. Like why call it the F ratio, right? The only reason we call it the F ratio is because Sir Ronald Fisher, right, developed it. And his last name began with F. That's the reason. Okay, so simple regression, multiple regression. Main questions asked in a simple regression. Okay, when we say simple regression, we're talking about one dependent variable and its variation being predicted or explained by just one independent variable. Okay, now in regression speak, the dependent variable is called usually either the criterion variable or the outcome variable. So if you hear dependent variable, criterion variable, outcome variable, all means the same thing. Okay? It's what we're trying to predict. The independent variable is called the predictor, or predictor variable. And you can have one or more than one. But in the instance that we're talking about right now, there's only going to be one criterion variable, one outcome variable. Okay. So the main question we're asking in a simple regression is, does a predictor variable x account for a significant amount of variation in a dependent or criterion variable y above and beyond what we would expect by chance? The null hypothesis would say what? That the predictor should account for how much variance? 0. That's right. That's the null hypothesis. The alternative hypothesis is that it should account for more than 0. Okay? And we're going to see this play out in our SPSS output. Second question is one of predicted value. The way that regression differs from a correlation is that with regression, we can actually try to predict the value of y once we know the value of x. So the information is meaningful to us in a predictive sense. Correlation doesn't tell us that. So if I said, Brooke, I got a question for you. You ready? Okay. I said, okay, variable x is correlated with variable y 0.50. Okay? I have a value of 6 on x. What should the value of y be?
3.
No. But that's a good guess, because you basically said, I'm going to take 6, just divide it in half, I get 3. But here's the thing. Simply knowing the correlation doesn't tell me anything about what the predicted value of y should be. Right?
Like how much of the variation is due to the other variable, but it doesn't tell you the equation.
Right. It doesn't tell you the equation. That's the key point. So it tells you the degree relationship, like we know from 0.5, that it's a positive, moderate relationship. But it doesn't give me a predicted value for y, because I don't have an equation. Does that make sense? Okay. So that's the key difference. So the question comes up, how are correlation or regression different? Well, the way to think about it is they're not really different. It's just that they are related to one another. Regression builds on correlation. So when you look at the SPSS output, you're going to see, the first part of the output, you're going to see is the correlation matrix, all the variables and how they're correlated to each other. And then after that comes the regression output. Okay? Okay, so this is a simple regression. When we go to multiple regression, when we say multiple regression, what we mean is there are multiple predictors, multiple x's, still only one y. Okay? So, the usefulness of multiple regression, first of all, does it make sense that the two x's might be correlated with each other? Right? Could very well be correlated. In other words, they co-vary with each other. So, if that's the case, they might also both co-vary with y. So you would get 3 correlations, right? 3 variables, 3 correlations. And they might all be correlated with each other. The thing is, the x's might account for the same variability in y. Right? So we've got to figure out which one's more important. Okay, which variable seems to account more so for variability in y than the other one. So as a result, is it the case that new predictor variables that are added in after x1 account for unique variability in y that was not accounted for by the first predictor variable? Okay? Or is it the case that, for example, x1 and x2 are highly correlated, so if you entered x1 into the equation first, and then you add an x2, x2 does not account for any more variation in y. All right, maybe x1 soaked it all up. Okay. The best way to understand regression is by going through examples. All right, do we have any business majors in here? All right, so a couple of them. Great. All right, so business majors, this is your time to rule. You get an example specifically for business. Okay, this is from a Harvard Business Review, 2015. Amy Gallo did a nice little example explaining regression as it could apply to business and to managers. So you might find yourself at some point being a manager. And the example she gave was if you looked at the relationship between monthly rainfall, so on the horizontal axis, this is an increase in rain per month in 1 inch units, okay? Monthly inches of rain. And here's sales of coats.
Coats, okay.
Coats, not cokes. Coats, okay. So what are we seeing in our scatter plot? How would you describe the relationship between the two? Yeah. Yeah, this looks a lot like a positive correlation. It looks linear. There's nothing about that looks curvilinear at all, right? So if we drew a straight line through it, we'd probably be pretty justified, in drawing a line that looks something like that. Does that make sense? Okay. So now I'm going to start throwing some terms at you. So hang in there with me. The regression equation is going to look like this. It's going to be y prime equals a plus bx. Okay? Y prime is our predicted value of y. That's what we're trying to predict. Like in this example, we're really interested in, given the amount of rainfall that we observe in a month, how many coats do we expect to be bought at the store? Okay? And for managers, that's useful because why?
Yeah, like when you're planning how much inventory.
Right, so inventory control, right? If you don't have an idea how many coats to buy, you can end up with a whole lot of coats or not enough, right? If you have a whole lot of coats, you expose them to liability. If you don't have enough coats, you lose sales. Right? So you want to make a really good prediction about how many coats to buy. Okay, so we're going to develop an equation based on this model. Now, this is y prime. Y by itself would be the actual value, okay, that occurred empirically. So this would be the number of coats that were actually sold given the rainfall. So there's going to be a difference between y prime and y. Does that make sense? As long as the regression line doesn't predict exactly the number of coats, there will be a difference, right? And we call that difference what? Begins with an R. Residual. Residual error, right? Error in prediction. So y minus y prime, I think that's, or y prime minus y, would be the residual, the difference between the prediction and the actual value. Okay. X is a predictor. In this case, our X is monthly rainfall in inches. And A is going to be the point where the regression line intercepts the y-axis. B is the slope of the line. Okay? So when we pop this scatter plot up, we now have a line that's in here to fit the data. And we use, the way we fit that line and pick the best line is based on what criterion?
The smallest R.
Say that again. Smallest what?
R squared.
Not R squared. You're close. It's the smallest something.
Sum of the residual.
Right. It's actually the sum of the squared residuals. Okay? So when we say residual, we're talking about this error right here. So the difference from this data point to the line is residual. Okay? If the data point's below the line, it's negative residual. If the data point's above the line, it's positive residual. Right? If you summed all the negative and positive residuals together, you get 0. Well, what does that sound like? Yeah, when you're doing sum of squares, right? Okay, so what we've got to do is take these negative and positive residuals, square them, right? And the line that fits the data with the smallest sum of squared residuals is the line that best fits the data. We call that the least squares criterion. Okay? The least amount of squares, okay, is associated with the best line. Okay, so here's y, the y-intercept. This is the value for A. Okay, so right here would be 200. The slope then represents, in this case, for every inch of monthly rainfall, there is an increase of 5 coats sold. So if the slope is 5, that tells us the amount of change in the dependent variable for every unit change in the independent variable. So for every unit of x, we get 5 unit changes in y. Okay? That's the same as saying for every additional inch of rainfall, we get 5 more coats sold. That's why the line slopes up and to the right. Okay? So, here's the question. Olivia, see, because you volunteered to be a business major, right? You're on the spot now. Let's say that in a particular month, I had 10 inches of rain. How many coats should I expect to see, given this equation?
250.
Excellent. 250 coats. Does that make sense? If I had 20 inches of rain, how many coats should I expect to sell? 300. Now, here's part of the problem, right? Here's part of the problem. You don't know how many inches of rain you're going to have until you've gone through the month. So how would you do your orders? You got to order 2 months in advance, right? How would you do that?
Look at like past historical data.
That's right. Historical data. That's exactly how they do it. So they look at historical data. They say, hey, it's October. In the past, we've had 8 inches of rain in October. Here's how many coats we're going to buy. Right? And they'll use a regression equation to do that. Okay. Which brings us to an interesting aside to sort of think about. All statistical inference is historical. Why would I say that? Think about it. All statistical inferences that we make involve history. Yeah.
You have to base all of this data that you're graphing to get your regression on historical data. There's no way to look into the future and guess what they are, because in that situation we didn't need this.
That's right.
Yeah.
So every inference we make about what to do in the future, what order you would make as a manager, right, for a future month, is based on data that were collected in the past. So your inferences about how correct you're going to be depend entirely upon the degree to which future events replicate past events, right? If there's sudden climate change,
If it's a particularly dry year, your regression equation is going to take you in the wrong direction. Now, there's no better way to predict that we know of. But nonetheless, simply because you're running the regression doesn't mean you're going to be right. Right? If you have a really dry year, your coat sales are down, trouble. Right? So, yeah, and that's true of all inference. The quality of inferences depends upon the degree to which future events replicate past events.
Let's say like you notice that over the past 10 years, like monthly rainfall is like decreasing. Is there a way to like predict like, that like downward trend in consideration?
You could add a correction term. Yeah, you could. You could do that. Yeah, I mean, the assumption here is that your data come from historical data in which there's no trend like that, right? There may be variability, but we don't expect that variability to be loaded in the most recent years, right? So, yeah, there are corrections that you can run for that, okay? If you have, enough data points, maybe you can just use part of the data set, okay? If you have enough stores, maybe you'll use part of the data set, okay? Okay. Does that make sense? Good. Okay, here's an example from your book. This is the relationship between what Caldwell calls GAE scores, which is a proxy for GRE, and graduate school GPA. Now, we've talked about this, and what's interesting is Caldwell gives you an example in which there's this huge correlation between GAE scores and graduate school GPA, which in fact there isn't, right? But as an example, may be useful. So, first thing that Caldwell will show you is the scores on X, scores on Y, then uses the z-score calculation for correlation, ends up with an R of positive 0.92. Who wants to tell me what an R of positive 0.92 means? .92 means what? Strong.
Strong positive correlation.
Strong positive? Okay, Kendall, you get the next one. What does R squared of 0.85 mean?
85% of the variance between X and Y is shared.
Right. Okay, good. So you have the interpretations correct. Now, what you'll notice in her data set, which should look weird to you, is you get this huge range of GAE scores, which doesn't happen in graduate school. There's not a huge range like that, right? This person isn't going. Okay. And then you look at GPA, and there's also a big range, right? The reality is failed, 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 failed. Most of those students fail graduate school. Right. So it's one way it's not an authentic data set. But here, when you plot it out, here's what it looks like. And we could draw a line through it, right? Now, we could draw any of a number of infinite lines through it. In fact, I could draw, for example, a line that looks like that through it, a red line. Does that look like it's a good fitting line? Why not?
Residuals aren't very long.
Yeah, we'd have a lot of residuals, and how do we know? Well, we compare the two lines, and that's essentially what SPSS is going to do. It's going to find the line with the smallest squared residual. So let's imagine I've got data for the black line, data for the red line, and then I start looking at every single data point. Well, here's one. Now let me calculate the distance to the black line, and I'll square it. And then I'll calculate the distance to the red line, and I'll square it. And you'll notice right away, there's a big difference, right, in terms of how close those lines were to that data point. Do it again for another one. We'll take a look at that point. Now that one's a little bit closer to the red line than maybe to the black line. Does that make sense? So I get all these squares for every data point, which represents squared deviations, right? Squared residuals. I sum up those squares, and if we just use those two data points, but we would, of course, extend to all of them, we end up with a 0.17 value, which is 0.14 plus 0.03 for the black line, 1.19 for the red line. So which line are we going to choose? Black line. Does that make sense how that works? Okay. Good. So that's the least squares criterion. The regression line with the smallest sum of squared residual error is going to be the line that is used in our regression mode. That's the best fitting one. Okay. So that takes us to multiple regression. What is it? Rather than regress the dependent variable on just one predictor, now we have a set of predictors, more than one. There's really no limit, okay? We could have 2 predictors, we could have 10 predictors, we could have 100 predictors.
Okay. We're going to inspect the correlation matrix first, and then we're going to go to the multiple regression. What does it accomplish? It's going to tell us a couple of things that are really important. The first is that it shows the amount of variability an individual predictor, or X, shares with a criterion outcome variable, Y, once we have controlled for the effect of other predictors. So this is the amount of unique variability that each X maintains with Y. Okay? It's expressed in two ways. One is using an unstandardized beta coefficient, or lowercase b. Okay. I'm going to be coming back to this in a little bit. The other way is using what's called a standardized beta coefficient. Okay? And basically, when we run the test, what we're going to be asking is whether this standardized beta coefficient differs from 0. Okay? Whether its value is different from 0. If its p-value is significant, we're saying that the beta value is large enough that it's accounting for significant amounts of variance in Y. Okay. When we have those predictors then that significantly predict variance in Y, we can put them together in a set and then see how much variability together they predict in Y. Okay. So it shows the amount of variability the set of predictors, significant predictors, share with the criterion outcome, and that's called R squared. Okay. And we'll talk more about that in the video tomorrow. We'll have a little bit more elaboration on that, but we'll walk through it today. You'll see the output today. So let's give it a go in SPSS. How are you doing? Any questions on that so far? Everybody good?
So the beta and the beta are for individual predictors, and R squared is for all of the predictors.
Yes, that's right. Yeah.
Can you go back to the slide for 1 second? Thank
Sure.
you.
Okay. Does that make sense?
So it's like main effect and interaction.
Kind of. Yeah, anytime you have more than one variable that's, well, that's a good question. Because what you're asking is how to determine when moderation is occurring using a regression equation. And typically, and I don't want to go into a lot of detail because it'll get confusing for everyone, but typically what happens is you run a series of regressions, okay? And you enter in different predictors. So let's say you have x sub 1, x sub 2, right? And you want to see if x sub 2 moderates x sub 1's relationship with y. You'd start with x sub 1, and then you do the next equation, the next regression equation includes x sub 2, right?
And then you do x sub 2 by itself.
Yeah, and so you've got it, there's a series that you have to go through, okay? Okay, so we'll give it a go in SPSS. So you watch the Challenger video, right? So look at this picture. What do you see in this picture that shouldn't probably be there?
There is fire coming out of the side of one of those rockets.
Right there?
Yeah.
Yeah. So what's that?
The leaky O-ring.
Right. So here's the issue, right? So there are O-rings per solid rocket booster. You can see it's actually separated into sections. You can faintly see the O-ring up here. You see the O-ring kind of right there. Right? You faintly see this, but it divides the solid rocket booster up into component parts. So this is a big thing. It's multiple stories, right? And the issue was that on the day of the launch,
in Florida, it was 31 degrees at Cape Canaveral. Okay, so really cold. In fact, NASA had never launched a shuttle when the temperature was below 50 degrees. This is the first time. Okay, so really cold. The O-rings are made of rubber, right? And when rubber gets cold, what happens? Yeah, it gets hard and brittle. But most importantly, it's not resilient, right? It doesn't reform to its original shape. 31 degrees, they decide to launch. A lot of heat going on in the booster, so what's happening to the metal in the booster? It's expanding, the O-ring's not expanding, so what has to happen?
There's a gap.
There's a gap, right? And if there's a gap, all of a sudden now you've got fuel exploding outward, oxygen mixing in. This shot was taken just within a second of the explosion. What's happening right now is this is all igniting, right? And then it exploded in a fireball. And when it went, it really went, right? So, big problem. This slide is impossible for you to read, but I put it in here, okay, so that when you're studying, you can go back over this just to appreciate some of the details. Just the highlights on this slide. There were a lot of discussions the night before about these O-rings. The engineers were really beginning to get frustrated because they were arguing with the NASA execs that at 31 degrees, bad things happen, okay? The NASA folks, the execs, were feeling like they'd been behind schedule on this launch, hadn't launched in a while, and they looked at data that seemed to suggest there was little to no relationship between the temperature at time of launch and the risk involved.
They
Okay.
had their sample size. Their sample was.
Sure.
Yeah.
Right, but the thing is, you have executives making decisions in opposition to some of the engineers, right? So no previous liftoff under 53 degrees. It was 31 degrees. When Challenger exploded, it was 12 miles up, right? And the crew cabin was found 10 miles out to sea and 100 feet of water.
So I have a really sad story about that, about what actually happened. So it looks like they all died when
Right.
it exploded, right? They didn't.
No. Yeah, in fact, that's just what I was going to say.
Yeah.
There's evidence that they manually deployed their emergency
Oxygen
air.
masks.
Yeah.
Yeah. So they were conscious for about 2.5 minutes because they went up an additional 2 miles.
Right.
To 12.
Right, and then came down.
Yeah.
Yeah, so they're on a
water.
ballistic launch, right? So
Yeah.
they're going to arc. So yeah, so that was a big thing, right?
There's no safety in place. If they had
Yeah.
like in case that this happened, and then like the front capsule had airbags that
Right.
like, or not airbags, no, it's very hard. Parachutes that
Ejection.
deployed, everyone would have survived.
Yeah, and folks have made that argument. Now, there's some debate over how long they stayed conscious, right? That they were conscious enough to deploy the oxygen, but with the depressurization, they don't know exactly how long afterwards. But there's some good reason, like I said, to think it was more than a marginal amount of time. It was long enough for them to realize what had happened.
Yeah, there's actually like an uh-oh that you can hear right before things cut
Right.
off, where they knew that it was starting to ignite.
Yeah.
And then the paper that I was reading was showing that, like, because of how little damage occurred to the cabin, there
Right.
wasn't that rapid depressurization.
Oh, interesting.
Yeah, that like you think would
Yeah.
occur. And if anything, maybe 1 or 2 people would have passed out, but it was
Okay.
actually highly unlikely. It was
Interesting.
It was the G-force of falling
Falling.
that would have made you unconscious, but
Right.
really the thing that killed them was 2,500 Gs of
Yeah.
force when they hit
Right.
the water.
Yeah. So, but send me that. I'd like to see that paper. So that'd be neat to see. So yeah. So anyway, so this gives you a little bit of detail. And here's some of the data that the engineers were looking at and the NASA execs were looking at. What they did is they pulled out, there were about 26 launches, something like that, prior to Challenger. Okay? They categorized and they extracted out data for every launch where there was what's called thermal abrasion of the O-rings, or a thermal event to the O-rings. The O-rings were damaged in some way. And then they plotted those particular events. There were 7 launches where that happened. They plotted that against temperature. And this is the graph that they ended up with. So the scatter plot, just ignore the grids, the scatter plot seems to show, you've got this sort of value here, but you also had 2 O-rings damaged at 75 degrees, okay?
So the vertical axis versus number of incidents, that just means the number of O-rings that had thermal abrasions. Down here's our temperature. And if we were to draw a line through this, very small data set, if we were to draw a line through it, maybe it slopes a little bit this way, but not much, right? I mean, we've only got one event here at a low temperature. And we also have an event here. This one kind of pops out at a higher temperature. So the NASA execs are saying, no, there's nothing really here for us to look at. Okay. What's the problem with this data set? It's small. There's another problem. Yeah, Shannon?
It doesn't even go to 32.
Yeah, we have no data at 31, right? That's important. Because, why is that important? Because your regression is a linear model, right? It's a straight line. It doesn't curve to the data at all. It's a straight line, right? So it's going to assume whatever line we draw here is straight for the entire width of our scatter plot, okay? Our data may not be linear though, right? If we have curvilinear data, our linear regression is going to make big mistakes. Okay, but there's another problem here. It's subtle. Let me take a little thinking about it. Think about how the data were extracted. Think about restriction of range. This is a tough one. I'm not expecting you to get this. If NASA engineers didn't get it at the time, it'll be hard for you guys to. Okay? Here's the thing. They only looked at cases where there were events, thermal abrasion events. They didn't include data where there were no thermal abrasion events. That's the rest of the launches. Look what happens to this graph when you include that data. Now what? How does that change the way you think about what's going on?
A lot more. It gives me a lot more concern.
Why? Medora, why?
Well, you see that the launches that were in warmer weather have no incidents whatsoever, whereas
Right.
the few launches that they did have in cooler weather all had incidents.
That's it. Look at this. Anything, sure, there were a couple incidents here above 65 degrees, but every launch under 65 degrees had an incident.
Is this what they were showing to the executives?
No, they hadn't analyzed the data this way, right? So this is kind of a subtle thing, but think about it. This is a restriction of range phenomenon, right? We didn't see the full range of the launches. We only saw part of the range. That led us in one direction on our conclusions. Once we saw the full range of outcomes, all of a sudden, man, this starts looking like a line that looks like this, right? Yeah, so all of a sudden that starts looking like an inverse relationship. Okay, well, Richard Feynman chaired a committee looking at, he's a physicist, famous physicist, looking at what happened with Challenger, and there was a series of investigations, congressional hearings that culminated in this statement by him, which is very famous. I remember when this statement came out. It's a famous moment in the history of this event.
So I took the stuff that I got out of your seal and I put it in ice water. And I discovered that when you put some pressure on it for a while and then undo it, it doesn't stretch back, it stays the same dimension. In other words, for a few seconds at least, and more seconds than that, there's no resilience in this particular material when it's at a temperature of 32 degrees. I believe that has some significance for our problem.
Now, there's a great movie that, if you get a chance, if you're interested in this, it's called The Challenger Disaster. It has William Hurt. And basically, Hurt plays Feynman. What happened during the congressional hearings was that the Reagan administration and the execs at NASA were pressuring Feynman to draw conclusions that it was hard to tell indeterminate why Challenger exploded, because they didn't want NASA to be
shamed by this. Feynman was actually approached when he was on a trip to Washington, D.C., and said, you can't publish your report the way you want to publish it. Okay, you need to say that the findings are inconclusive. He flew back to California. And at first he said, okay, I understand why you need to do that. He flew back to California, and then he contacted the folks in Washington and said, look, if you don't publish my findings, I resign from the panel, and then I tell the media why I resigned. Right? So he stood up for his ethics, right? At great potential professional cost to himself. He stood up for it, and eventually all the findings were published. Okay? So Feynman has a really interesting history just in and of himself outside of this. But it's a great film that deals with scientific ethics. So for those of you who are interested in that, I'd really encourage you to watch it. I think you might be able to get it on Netflix. Yeah.
I found the statement. It's by Dennis E. Powell.
Mm-hmm.
When the shuttle broke apart, the crew compartment did not lose pressure, at least not at once. There was an uncomfortable jolt, but it was not so severe as to cause injury. This probably accounted for the "uh-oh" that was the last words he heard on the flight deck tape recorder. As they were feeling the jolt, the 4 astronauts on the flight deck saw a bright flash and a cloud of steam. The lights went out, the intercom went dead, and after a few breaths, the 7 astronauts stopped getting oxygen to their helmet. Apparently, someone leaned forward and turned on the air pack shuttle of Michael Smith, one of them, because it was in a place that he couldn't reach. Even though some of them weren't activated, the crew compartment did not rapidly lose air pressure, so they would have just been able to lift their masks to breathe.
Okay.
So this is supported by the fact that they actually got the masks back. One of said masks actually had ears in it.
Okay. Well,
Yeah.
we'll just leave it at that.
I'm not going to go
But so,
into
yeah,
it,
send it to me. Send it to me. I can post that.
But like I
People
said,
want to take a look
it
at
actually had body
Yeah.
parts in the masks. So
Yeah.
we're not going to talk about
Yeah.
that.
Okay. So that's some imagery that I probably don't need in my head right now, but
Sorry.
that's okay. Okay, so let's move on to actually looking at the SPSS output. Hold on. There we go. Okay. All right, so this is a relatively small data file, and there are 5 variables in it. Num O-ring risk, that's just the number of O-rings at risk on a given flight. That's a constant because there were always 6 O-rings, so not a variable we're that interested in. Num therm is the number of O-rings experiencing thermal distress. So that can range from 0 to 6. Temperature was launch temperature. Okay, most of those temperatures were up in the 60s and 70s. Leak pressure, now this is one that takes a little explanation. A leak pressure check for the shuttle involved NASA exerting pressure just prior to launch within the solid rocket boosters to test the strength of the O-rings, because they knew that that's a potential weak spot. So they would pressurize those chambers, and in the early days of the shuttle, the pressure was at 50 pounds per square inch, and then by the time they got to the Challenger disaster, it was up to 200 pounds per square inch. The criticism was that when you get to that high of a pressure check, that you might actually damage the O-rings. Okay, so is there a relationship between the test itself and thermal abrasion? And then finally, flight is the temporal order of flight. So here's what the data look like in the data sheet. Here's our outcome variable, dependent variable, or Y. That's what we're trying to predict. There's the temperature and leak check pressure. Okay? You run the analysis here, and this is what you'll be doing. We'll run through this analysis to start lab tomorrow. Here's our dependent variable, number of O-rings, experiencing thermal distress, and there's our 2 predictors. We're going to check off model fit, R-squared descriptives, and the regression coefficient estimates. These are going to be our betas. Here's the output. So the first part of this output is the correlation matrix. So it shows the relationships of each variable with the other variables. Okay? So the correlation between launch temperature and number of O-rings experiencing thermal distress, negative 5.511. Negative 0.511.
Who wants to tell me what that means? A negative 0.511 correlation between launch temperature and number of O-rings experiencing thermal distress. Sally?
It's like a mild to moderate negative relationship. So as launch temperature goes down, there's going to be more O-rings experiencing thermal distress.
Exactly right. Perfect. Okay. Here's the correlation between leak check pressure and O-rings. It's 0.285. Who wants to tell me what that means? What do you think that means? Yeah.
There's a 0.285 positive correlation with the O-rings experiencing thermal distress if they had been for how much pressure they were put on under during testing.
Right. Yeah. So as the pressure went up, right, we did see evidence of some increase in distress. The magnitude is not as large as with launch temperature, right?
It's still
So
good enough.
still not bad, right? So when we come down here, we look at whether or not these correlations are significant. Launch temperature has a p-value of 0.006. Leak check doesn't, 0.09, but that could be because of small sample size. You got power issues. Okay.
Did you calculate power?
Okay. 0.04 correlation between leak check and launch temperature. Very little correlation there. Okay.
I mean, they shouldn't be.
Shouldn't be, right? So there shouldn't be a correlation between the two. So that's non-significant. Okay, next part of our output is really the meat of what we're looking at for the entire testing of the model. Okay, what SPSS does, it's going to enter in both predictors, right? And it's going to say, okay, what's the combined correlation when both these predictors are included in the model? And there's a correlation close to 0.6. Okay, R square of 0.35. So who wants to tell me what the R square means? R square is,
35% of the shared data.
yeah, the variability, right. Yeah, so when we take into account these predictions, they account for about 30.35 or 35% of the variability in O-ring distress. That's a lot. I mean, 65% is due to something else, but 35% can be accounted to these variables. We come down to our ANOVA, and it's at 5.490, significance 0.013. Basically what SPSS does is it creates one model in which there's a null effect, okay, when there's no effect of the predictors on the dependent variable, compares it to our regression model right here, and then asks if they're different from one another in terms of the amount of variability they're accounting for. If you get a significant result here, basically it's saying this R square is accounting for a significant amount of variability. Okay? So, we're going to get an F ratio. We're going to get a p-value for it. R square effectively represents our effect size. Okay? So this is the amount or the magnitude of our effect. Here's the likelihood that the result is due to chance or measurement error. Okay? Does that make sense? Okay, and then the question is whether both of these variables are significant predictors or not, or just one. So then we go to the coefficients table. Okay? And what you're going to see in the coefficients table is two columns related to unstandardized coefficients, and then one column related to standardized coefficients. Here's the difference between the two. Remember that the coefficients are the weights for the x's. Okay? The b value. Okay? So it represents the slope in the line for any given variable and its contribution to that line. So when we see negative 0.049, the way we interpret that for the unstandardized coefficient is for every 1 degree increase in launch temperature, there was a 0.049 decrease in number of O-rings experiencing thermal distress. Does that make sense? For every pound of leak check pressure increased, there was a 0.003 increase in number of O-rings experiencing thermal distress. Is that good? Okay, so what unit of measurement are we talking about here for launch temperature?
Degrees Celsius?
Say that again?
Degrees Celsius?
Actually, I think these are in Fahrenheit.
Oh, sorry.
Yeah, but you're on the right track. How about for leak pressure?
PSI, pounds per square inch.
Yeah, pounds per square inch. Those are different scales, right? So, what's the problem that occurs if we have different scales?
How do you graph that?
But
How do you graph that?
well, you can graph that, but it gets a little bit tricky. They're variables that are not directly comparable because they're not in the same scale or metric. Okay?
This is
So-
why we use metric.
So how do we get them into the same scale or metric? What do we need to do?
Metric system again.
No, you don't have to go that far. You can do this mathematically. In fact, you guys did this at the beginning of the semester. If you were to take, say, think back, way back to like week 3, and I might say, okay, Johnny had a 60 on an algebra test. Mary had a 120 on a, there we go, what? Say that again, but it just all came back in a bad memory, didn't it? What? Standardized scores. So we might convert them into what?
Standard scores.
Yeah, standard scores, but you have to do what beforehand? Convert them into like, you're out in the savannah, there's a lion, there's a hippo, then there's an animal with black stripes and white skin. Zebras. And the first letter in a zebra is Z-scores. Okay, so we need to convert to standard deviation units, right? So that's what a standardized coefficient is. Everything gets converted to standard deviation units, okay? So these become your standardized weights. And a standardized weight says, okay, change independent variable in standard deviation units when we change the independent variable by 1 standard deviation. Does that make sense? So, for every 1 standard deviation change or increase in launch temperature, we see a negative 0.52 standard deviation decrease in the number of O-rings experiencing thermal distress. You guys with me? Everything's now in standard deviation units. So we can compare leak check pressure and temperature directly to each other because they're both in standard deviation units, as is O-ring distress. Okay? For every 1 standard deviation change increase in leak check pressure, we see a 0.31 standard deviation increase in number of O-rings. Okay? Of these two, the only significant predictor is launch temperature. Okay? Why? What is it looking at? It's looking at these beta values, and it's asking, are those beta values different enough from 0, which represents our null hypothesis? If they're different enough from 0 not to be accounted for by chance or measured error, you're going to get a significant p-value here. Does that make sense? So we're actually testing these betas. There's a t-test that's run that we're not going to go into details on. Gives you a significance value. The main point is, the farther these values get from 0, positive or negative for the standardized betas, the more likely you're going to reject the null and end up with a significant p. Now, we had a 0.306 right here for leak pressure, but that wasn't enough, probably because of the small sample size.
Yeah,
Right.
if it was like 0.9, then I would think it was due to the sample size. But it's only 23 samples.
It's small, yeah. So we'd like to see a bigger data set. Typically with regression, you have to have a fairly large data set to feel comfortable running it. 26 is really, really kind of small. Even for two variables, we'd like to be up somewhere closer to 75 to 100, somewhere around there. Okay, so now the main question is, we need to create an equation that predicts number of thermal distress O-rings, right? So we're going to go back to our regression equation. Remember that was y prime equals a plus b times x, and then you repeat for all the predictors. So that would be 3.33 plus negative 0.049, right here, times 31. Okay, we're back into our original metrics now. 0.003 times 200, which was the PSI for Challenger. You add these together, and if you take those two variables into account into your equation, even though PSI is not significant, you add that in anyway, you get 2.411. What does that number mean? 2.411 means what? What is the Y being predicted?
Failed O-rings, so 2.41 that should have failed.
That's right. Yeah, or at least had abrasions and were in danger of failing. To give you some context, let's go back to the original scatter plot. Where does 2.411 fall on the vertical axis? Right? It's higher than all but one of the events. Does that make sense? I'd say we got lucky right here. Right? So 2.411 would be up here. So the regression equation is predicting some the second most number of abrasions in the history of the program. Okay? That should have been an alarm bell. Okay, now, what if, in reality, it's not a linear relationship? It's a curvilinear relationship. Right? Because if you think about it, here's what we're looking at. The data cloud looks kind of like this, right? And so the regression equation goes through this data cloud. So it's flat down here, going up this way, goes through this regression, and the lowest temperature is what, like 53 degrees? Does that make sense? Okay, so the regression line basically is a straight line going through this cloud. Okay, but what if we have a curvilinear relationship and the actual data would look something like this? In other words, you get under 53 degrees and you go through the roof on the number of abrasions. Right? Then, where is our residual error? Do we have positive or negative residual error?
Positive.
What?
It's a positive since it's above the line.
It's above the line. You don't want positive residual error in this area, right? Because positive residual error means your regression line is underestimating the number of thermal abrasions. So, real possibility here that by using a linear regression line, we could have been trying to fit a linear model to curvilinear data. So even though the regression tells us to expect 2.411 abrasions, O-ring abrasions, the reality could have been 5 or 6, right? If it's a curvilinear relationship. Does that make sense?
Does it know how many O-rings?
I don't know. That's a good question. I don't know if they recovered the O-rings or if they, my guess is in that heat they may have just vaporized. But
They recovered the capsule and they recovered bits of the
solid rocket
Yeah.
containers. And so one of the other things is the proof of the rapid depressurization not happening is the cap will have buckled inward,
Oh, okay.
and that didn't happen.
Okay.
Yeah, it just broke apart when it hit the water.
So anyways, all right, here we go. So big picture. Regression is built from the foundation of correlation. Does everyone see that? Right? We're looking at an associational model. It's all part of the general linear model. ANOVA, t-test, regression, they all come from the same place. It's all an additive general linear model. Okay? But typically, we'll use ANOVA and t-tests in highly experimental paradigms where there's a lot of internal validity to the experiments. Okay? And we're more likely to use correlation regression when we don't have so much control over the variables, but we want to see associations between them. Okay? Regression gives us the ability to predict scores on y, given what we know about x. Those predictor variables often are correlated, and we'll have to test for that. It's called multi-collinearity. Big word. We'll talk more about it in the lab video tomorrow. Okay. We just generally don't want a lot of highly correlated predictor variables because they're not useful to us. Oh. It's a little unpredictable. Okay, least squares criterion tells us which regression line is the best fit of the data. Everybody good on that? Good. Multiple regression controls for the effect of other predictor variables. Everybody good on that? So when you run a multiple regression, you see the effect one variable has on explaining variance, and the criterion variable, once you've controlled for the other variables, you understand how much the other variables predict. And then our main indices of interest, we're going to be looking at R squared, adjusted R squared, beta, could add p-values up there. But we're going to basically be testing for whether the model as a whole significantly predicts variability in our outcome variable, and then the contribution of each individual predictor. General rule of thumb, the more predictors you have, the bigger your sample size needs to be. Okay? There's no exact rule to how big it should be, but you'll probably be okay. You know, if your data, your number of observations is 20 times the number of predictors you have, you should be okay. You know? So for 2 predictors, you'd like to have a minimum of 40 cases. For 3, 60. For 4, you'd like to be up to 80. Okay? But there are different opinions on how many you actually need to have. I think that's it. That's it. Any questions? That's kind of interesting stuff, right? I mean, you know, tragic case with Challenger, but, you know, I think it's good we're still learning lessons from it. Yeah?
There are multiple p-values, so when
Right.
looking at the significance of, do we want to look at the coefficients table solely, or do we hold the significance of it?
Well, the p-value that you look at for the R squared is in the F ratio table. So you look at that ANOVA table, and it's the p-value associated with F. That tells you whether the model as a whole is significantly better than a random model.
Okay.
And then for the coefficients table, you'll find a p-value for each predictor. And that tells you whether the predictor individually accounts for unique variability.
Okay.
Okay?
Thank you.
Okay. All righty. I may or may not see you tomorrow, I guess, right?
Yeah,
So.
I might come in just to run